So, my dear students, now in this lecture we are going to discuss about design of Mod-6 counter using T flip-flop. So, we are designing Mod-6 counter using T flip-flops. Okay. So, what is Mod-6 counter? Mod-6 counter will have a state transition which is going from 0 to 1 to 2 to 3 to 4 to 5. This is called state transition. This is how it is moved from one state to the other state. 5. State transition diagram. This will help us to get the state table, right? So let us write the state table. State table. What it consists of? Current state. How many flip-flops required? 2 power n. What is that? 2 power n should be greater than or equal to capital N. So 2 power n should be greater than or equal to 6. N equal to 3. N equal to 3 is 8. 8 is greater than or equal to 6. Fine. So 3 flip-flops required to design Mod-6 counter. To design a Mod-6 counter, what is required? 3 flip-flops required. Let's say the flip-flops are ABC. So let's say QA, QB, QC. QC plus 1, QB plus 1, then QA plus 1. Then TA plus first write TC. Let me erase this. This is a TC, right? TC, TB, then T. So when present state is 0, 0, 0, 0, what I am going to get the next state as 1, 0, 0, 1. Present state is 0, 0, 1. Next state is 0, 1, 0. What it means? 0 to 1, 1 to 2, 2 to 3. This is same thing. Whatever there in this transition diagram, we are putting in state table. Why? What we are saying that if for all I will design a counter, this is how it will move its state. That's the reason why it is called a state table. So if the present state is 0, 1, 0, next state will be 0, 1, 1. If present state is 0, 1, 1, next state will be 1, 0, 0. If present state is 1, 0, 0, next state is 1, 0, 1. That means up to 5. If the present state is 1, 0, 1, next state is exactly 0, 0, 0. For present state 1, 1, 0, next state is doesn't matter, doesn't matter, doesn't matter. Similarly, for 1, 1, 1, what exactly happens for 1, 1, 1? For 1, 1, 1, doesn't matter, doesn't matter, doesn't matter. 1, 1, 1. So 1, 1, 1. Your output is doesn't matter, doesn't matter, doesn't matter. Done. Now what I need to do? I need to compare QC the way we did it earlier. Right? QC. Compare with QC plus 1. Then write TC. 0, 0. Is there any change? No change. Means TC 0. You know the excitation table, right? Which excitation table? T flip-flop excitation table. How it look like? QA, sorry, Q in general. If I say QA, QA plus 1, I need to say QA plus 1. Then TA. 0, 0, 0, 1, 1, 0, 1, 1. Whenever they are same, it is 0. When there is a change, input should be 1. So whenever there is a same, input should be 0. Whenever there is a change, same, 0. Is it same? 0. Is it same or change? Change, 1. Is it same or change? Same, 0. Is it same or change? 1, 0. 1 0 means change 1. 1 don't care, don't care. So don't care, right? Similarly, okay, I can write it for TB. For TB also, what I will get? In similar lines I can write. I will get 0 1 0 1 1 0 0 1 0 0. Don't care, don't care. Similarly, if at all you get this 0 1 1 0 1 0 0 1 1 0 0 1 1 0. So everywhere it is changing. That means J 1 1 1 1 1. Don't care, don't care. Now what I need to do? I need to get the expression for TC, TB, TA in terms of QA, QB, QC. What are these? This is called flip-flop inputs. Now what I do is, I take a K-map. From the K-map, I try to get the expressions. What is this? What are the variables I have? I have QA, QB, QC. 0, 1, 4, 5, 7, 6. 0, 1, 3, 2. 0, 0, 0, 1, 1, 1, 1, 0. From K-map, you know. So what I need to enter those values for which? What exactly they don't care, sir? 6 to 7 don't care, sir. Okay, these two. What about these values? 0, 0, 1. What is 0, 0, 1? For 3 it is 1. For 3 it is 1. For rest of them it is 0. For 3 it is 1. Next. For 5 it is 0. For 4 it is 0. See, this is 4. This is 5. So 4 it is 0. 5 it is 1. So this is how exactly. Now what I can do is, I can combine these two, and also I can combine this two. From that I can write the expression for what sake I am writing this. This is for TC. I have entered the values of TC. I will get expression for TC. So the TC turns out to be QC QA plus QB QA. Similarly, what I can do? I can take the K map for TB and I can get the expression for TB. Similarly, I take one more K map. Okay. What I do is, I try to get the expression for this is for TB, this is for TA. Enter the values of TA. What of this that is the TA? All are ones. These are don't cares, rest all are ones. So what is TA value? TA is equal to 1. Directly answer. With respect to TB, if at all you see, in TB you have only two ones. What are they? It is 1 for 1. It is 1 for what exactly this value? This is third value. So it is 1 for 1 and also it is 1 for 3. So 0, 1, 3, 2. It is 1 for 1. For 3 it is 1. 6, 7. This is 7. This is 6. This is 4. This is 5. Okay. So these two are dot pairs. So what I can do? Simply I can combine these two ones. These two ones I can combine. So what is the expression that I am going to get for my TB is going to look like? What exactly the value that I am getting? Of course it is QA, QB, QC, QA, QB, QC, from which I am going to get the expression for TA and TB. TA is equal to 1, whereas TB, what is the value? It is not a QC bar QA, yes, it is QC bar QA. Okay. From these expressions, even I can draw what exactly I can do, you know. I can go for hardware circuit diagram. So what is the hardware circuit diagram? I take T flip-flop. In the last problem I didn't do it because it was a length, it has become lengthy video. So to reduce the lengthy, just I didn't show it. But in this example, I am going to show the hardware realization from the results what I have got. Now It is synchronous counter. What is in the synchronous counter? All will have a common clock, common clock, common clock, common clock. So this is clock input. That's fine. Now TA is equals to 1. TA is equals to 1. What is mean by TA? TA, let's say this is flip flop A. Let's say this is flip flop B. Let's say this is flip flop C. Now what is that? This TA, input TA. Okay, let's say it is input TA. That input TA should be connected at 1. What about TB? TB is QC bar QA. So this is QC. Here I have QC. This is QC bar. You take this QC bar and you take this QA. Of course, this is QA. This is QA bar. So instead of writing the diagram, like instead of drawing a line, I simply take a gate, AND gate, for which one of the input is QC bar. QC bar is available from here. And another input is QA. It's available from here itself. So one is QA, QC bar. Output I am connected to TB. Now what about the next? What is that TC? TC is this. So I have QA, QB. I have QA, QC. So what I do is I'll take two AND gates. One will give you one AND term, another one will give you another AND term. I will OR them. Upon ORing, I will get a value that I am going to connect it to what is known as TC. What are these inputs? One is QA, another one is QC. One is QA, another one is QB. QB. This is hardware circuit. So QA is your output, QB is your output, of course. This is QB, that is your output. QC is your output. So if you go and give the clock pulses to this, what is going to happen? It will move from 0, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. Then it will continue with 6. This is what exactly the circuit diagram for Mod-6 counter using T flip flop. You can see the amount of labor reduced with respect to the design. If I take JK flip flop, okay, it looks like complex. 6 K-maps required, only 3 K-maps required. Okay, easy to design. So generally for any counter design is asked, go for T flip flop. If problem specifically in the problem, if it is mentioned that implement using JK, you can go for JK or SR or D. But if nothing is mentioned, better to use T flip flop. I hope with this you have got how to design, because I gave two examples. With this background, you can design mod 3, mod 4, mod 2, mod 7, mod 8. Okay, whatever it may be. Is that fine?